In this video, we will be learning about the assembler, its functions, and data structures that is being used. So here we will be considering a simple SIC assembler. So in main assembler functions, it includes translating the mnemonic operation code to their machine language equivalent and assigning machine addresses to the symbolic labels. So the input given to the assembler will be a source program containing mnemonic codes and the some symbols in the form of labels or any other symbols. It will be fed as input to the assembler. Assembler, it generates an object code by giving some machine language equivalent to the opcode and also assigning some address value to the symbolic labels. It makes use of some directives called as assembler directives, which are considered as pseudo instructions because they provide instruction to the assembler itself. They are not translated to any machine language equivalent. So some of the assembler directives that is used are start, end, byte, word, RESB, RESW. These are some of the assembler directives that is being used. Start, it specifies the name of the program as well as the starting address. And end indicates the end of the source program. Byte is used to assign some byte constant, and word is used to assign some numeric constant value to some label or some symbols. Then RESB and RESW, it is used to reserve bytes and the words based on the operands that is given. End of record will be used, which will be indicated using a null character, and end of file will be considered as a zero length record. End of file will be considered as a zero length record. So we will be dealing with a program like this. So in their module, it will be dealing with the same program. The purpose of program is to write some record onto a from an input device, and that input device will be represented using F1, and copy that record to an output device which will be represented using 05. Here at the end of the file, it will be writing EOF on the output device. EOF will be written on the output device, which indicates the end of the file. Then we make use of some data transfer operations, RD, WD, read data and write data. So a buffer is used to store the record, and from the buffer it will be given to the output device. So end of each record is marked with a null character 00 in the hexar form, and end of file is indicated by a zero length record. Subroutines that is being used is RD-REC, WREC. In order to jump to a subroutine, JSub is used. Return from the subroutine, RSub will be used. For any nested jump cases, we will be making use of linked register in order to return to the main program, calling program. And coming to the example program, here this indicates start is an assembler directive, copy is the name of the program, it indicates a starting address 1000. So the program name is copy and the starting address is mentioned as 1000, which means from the next instruction onwards, it will be starting with the address 1000. Okay, so first this instruction will be starting with the address 1000. If no address is being given, then it will be assumed to be as 0. So in order to maintain this, we will be making use of the data structure that is called as LOC CTR. Location counter, LOC CTR. The location counter, it helps in maintaining the addresses of each instructions. Then first is the label. So this column, it indicates the label, this column indicates the opcode, and this one will be the operand. Okay. So if there is any label, it means that these labels will be assigned with some address value. So here first STL writ address. What does that mean? Stored to the link register some value that is stored in the writ address, which means the next statement will be a jump subroutine. Jump to a subroutine case will be coming next. Here comes the jump subroutine. To which subroutine needs to jump? RDREC. So for any jump subroutine instruction, we are making use of a link register. Okay. Then here again we will be having RDREC as one subroutine. From this onwards, it will be a subroutine to read the record. And here WREC is the second subroutine. From here onwards, it will be used to subroutine for write record. Okay. So in main program, here you will be having a jump subroutine to the write record also. Okay. So here we are making use of this link register. Why? Because in this routine we will be reading the read record, and also it comes under a loop. So after reading the read record, in the same loop we will be encountering with the write record also. So for that purpose, before that itself, you are making use of the writ address, because there is a chance of calling one in the same loop. You are calling two subroutines. So link register is also used. Earlier we have learned that link register will be used for nested subroutines. So here inside the loop we are calling the two subroutines, so we are making use of the link register. So read record, which means RDREC is to read the record that is written, that is stored in the buffer. So length will be the length of the bytes that is stored in the buffer or written. Then it compares whether it is equal to 0, whether it reaches to the 0. That is, if the length of the record is 10, means 10 records need to be read till it reaches 0. And if it reaches 0, end of file, jump if equals end file. What does that end file indicates? EOF is loaded to the accumulator, and from the accumulator it stores the value to the buffer. Okay. EOF will be loaded to the accumulator, and from the accumulator the EOF will be stored to the buffer. So buffer will be storing all the information that is written or that is read from the input device. Okay. A buffer will be having the information that is that is taken from the input device. It will be placing it on the buffer, and from the buffer it will be loading to the output device. So this is the case with the main routine. So read record In this read record, you will be having an index register 0. That is one by one you need to read the files that is written from the write record. Okay. So before reading, we can consider the write record. So in that LDX 0, it checks, it fetches the data from the fetches the data from the F1 and LDA 0, that is storing the value 0 to the accumulator. Then test for the input device. Input device, if it is ready or not. Jump if equals R loop. That is, it loops inside this statement until the input device is ready. If it is equal to 0 means it again loops inside the loop. If it is not equal to 0, what it does, it reads the input from the input and compares whether it is 0. That is, whether it reached to the end of the record. If it is equal to 0 means exit. What does exit means? Store the index register value, that is the X register value, to the variable length that is reserved for storing the 3-byte information, that is the length of the record. Okay. So if it is not equal to 0, that is if it doesn't reach to the end of the record, means store the character to the buffer. Buffer is the place where the information that is read from the input device is stored on the buffer. Then increment the index register value and checks for the maximum length. So maximum length here it is assigned to be as 4096. 4096 bytes is the maximum length. Jump if less than R loop. If it is less than 4096, it jumps to the R loop. Else, what it does, it exits from the loop and returns to the calling program. Okay. After returning to the calling program, what all things you will be getting? You will be getting the return address, that is return subroutine. It will be coming to the here it will be coming. So here what it is, length you will be getting, that is stored here, maximum length. Index register, it will be storing the value of index register to the variable length. That length will be stored in the accumulator and it compares whether it is equal to 0. If it is equal to 0 means it understands that it reached to the end of the file, and what it does, it jumps to the write record. Okay. Why? In order to read, write to the output device. Else what it happens, it will be reading the record. The loop continues until it reaches to the 4096 bytes. In write record, similar is the case. Index register will be 0. It will test the output device. Loops until the output device is ready. Character by character to the buffer, it will be loading. Then write the data to the output. Output will be represented using 0, 5. Then increment the index register and compares with the length. If it is less, W loop. So looping will be done until it reaches to the end of the record. That is a maximum length, that 4096, or the length of the record that is written by the input device. So this is the structure of the program, and end of the program, any directive will be used to indicate the end of the program. First will be having the starting address of the program. That's why here it is given as first. So this program will be used entirely in the module, so that the translation of addresses and everything will be based on this program. Thank you.